Welcome to AI Explains. Today we are looking at the European Space Agency's Gaia mission, and honestly, the best way to get your head around this is to stop thinking of it as a standard telescope.
Right, yeah, it's not really like Hubble or the James Webb.
Exactly. It's not taking pretty portraits of nebulas.
No, it's a surveyor. I mean, its whole job is to build the most precise 3D map of the Milky Way ever attempted.
And the scale is just silly. Gaia is charting over 1 billion stars.
It is a staggering data set. But the number that really grounds you is that those 1 billion stars, that represents only about 1% of our galaxy's stellar population.
1%.
Yeah.
That really puts the whole space is big concept into perspective for you.
Oh, absolutely. But Gaia isn't just counting dots, you know. The goal is to figure out the galaxy's life story, its composition, its formation, and its evolution.
Right, which brings us to astrometry. That's essentially measuring position, distance, and motion, right?
Exactly. By tracking how everything moves over time, Gaia is effectively building a dynamic movie of our cosmic history rather than just a static snapshot.
To do that, though, the hardware has to be incredibly specialized. I was looking at the payload module, and it's strange. It uses two identical telescopes, but they aren't pointing at the same thing.
No, they face completely different directions. They're separated by a very specific wide angle, 106.5 degrees.
The basic angle.
Right, the basic angle.
And that angle is the key to the 3D part, right? Because if you only look in one direction, you mostly just know where stars are relative to their immediate neighbors.
That's the limitation of a single view, yeah.
Oh.
But by measuring the angle between stars seen by these two different telescopes simultaneously, Gaia creates a rigid frame of reference.
So it allows for absolute parallax.
Exactly. It connects stars across the entire sky to calculate true distances for you, not just relative ones.
And catching all this light is a digital retina that is basically the biggest digital camera ever flown in space.
It's massive. It's a mosaic of 106 camera sensors stitched together to create a single image with 938 million pixels.
Almost a billion pixels. But here is this major engineering headache. The satellite is spinning the entire time to scan the sky. It does a full rotation every 6 hours.
Right.
Usually if you spin a camera while the shutter is open, you just get a blur.
You definitely would. But Gaia uses a neat trick called time-delayed integration. As the satellite spins, the image of a star drifts across the sensor.
Okay.
So the electronics actually move the recorded data across the chip at the exact same speed as the drift.
Wow, so the data tracks the image electronically while the satellite moves mechanically. That allows for long exposures without the motion blur?
Precisely.
But this brings us to the precision required. If you're measuring tiny angles to get that 3D depth, the spacecraft can't wobble at all.
Stability is everything here. The spacecraft has to be thermally and mechanically rigid. They actually use a laser interferometer called the basic angle monitor just to watch that 106.5 degree angle.
To make sure it doesn't shift.
Right, it detects changes as small as picometers.
Which is atomic scale. If the angle changes by the width of an atom, the map is off.
And while holding that incredible stability, that massive camera is doing 3 jobs at once. First, the astrometry we mentioned, pinpointing location.
Then there's the photometry. It uses blue and red photometers to split the light, which tells us the temperature and chemical composition of the stars.
And finally, the radial velocity spectrometer. This measures how fast bright stars are moving toward or away from us, the Doppler shift.
One detail I loved was the data transmission. You have this spacecraft that needs atomic-level stability, which means you can't have a big mechanical dish antenna swiveling around to aim at Earth.
The vibration would completely ruin the images. It would act like a blurred photo.
So instead, they use a phased array antenna.
Right. It uses electronic beam steering to shoot the data back to Earth without a single moving part.
It's basically a self-calibrating machine.
That is building a model of where the galaxy came from and where it's going. And importantly, this isn't secret data. A consortium called DPAC processes it, but then it's released publicly. The whole world gets to study it.
It is the most comprehensive map of our home we have ever built. But it won't leave you with the thought we started with. We have mapped 1 billion stars.
Which is just a 1% sample.
Exactly. If this level of complexity in history is what we find in the 1%, just imagine how vast and complex the 99% of the Milky Way is that remains unmapped. Thanks for listening to this deep dive.